This is a comparatively much smaller project than the last one we heard about. You see the partners here. It's Luleå University, 6, Aalto University, Futurize, and we have an SME in Cybercube. And we're working with efficient IoT content for a horizontal application space. And what do we mean with this? Well, we see that IoT, it has the potential really to offer a market of micro content, where there are billions of devices that can act as content providers. Fairly different from the today notion of cloud, where it's fairly centralized still. However, we see some challenges in opening this market, and today we have a lot of stovepipe vertical lock-in from IoT devices to cloud services. So if you're a company providing services in this space today, you typically have control of everything from the devices up to the actual cloud service that you're delivering. And we want to break that up, actually, opening this market for a new model. We have a challenge of scalability to billions of devices, and we have the challenge of resource efficiency, because those devices have limited IoT battery capacity, sustainability, and so on. Fourth bullet there is important, the intermittently connected IoT devices. You cannot expect that all IoT devices should be connected all the time. It consumes power, and in some cases there is not coverage all the time. And we have the security and trust challenge. So in this space, we wanted to look into how can we define solutions that are resource efficient, sustainable, and also business effective. And here it's important to point out that while lock-in is quite effective for some enterprises in the early phase, they can dominate the market basically by locking it in. This is typically not effective for the general market growth. So we see we want to open a horizontal platform where small enterprises and startups also can enter the scene. And our innovation and business approach in this project is first, we work from the conceptual level on an architecture for efficient IoT content delivery. And we have chosen to work on top of information-centric networks. So this is a community work, and primarily we're working in the IRTF, in the ICN-RG draft. Börje Ullman is one of the chairpersons there from Ericsson. He's sitting here. And we have also chairpersons from Cisco and NEC there. We've also published a paper. It's actually appearing in January in CCNC 16. So you can find more information there. I'm just giving a summary in this talk. And we also work with simulation and emulation frameworks to basically gauge how efficient this approach is. The second here is more important for IoT Digital. We have 2 commercial proof of concepts also. One of them is about Internet of Things in an underground mine, where we have very challenging network conditions, a lot of interference. We have not consistent connectivity, but it is in a small scale. Number B there is an IoT and mobile devices in an office or smart city environment. That's quite different. So I'm going to explain all these, the number 1 and the 2 flavors of number 2 in this talk. But before I go into that, I want to just summarize the benefits of ICN. Why did we choose information-centric networks at all? Well, first of all, because you name data, not devices. The current internet, you address specific devices. But in many cases, you may have many IoTs acting as sensors. And if I, for example, want to have the temperature of this room, I'm interested in the data temperature in this room. I don't care which of the sensors actually are providing that data. ICN also provides caching in the network. So this means that we may not require that IoT devices are connected all the time. It's a decoupling from publisher and consumer. So once the IoT device has sent its data to the network, it's there, hopefully, in the cache. So you don't need to have consistent connectivity up and running. So you fetch once from the IoT device, and this can be used by many applications in that case. No lock-in, really. So this is the network. The network never changes any data. The purpose of a network is just to transport the data. So it's important. We can have an overlay on top of this. You can build servers that collect IoT data from many devices, maybe do data analytics, and then can republish this data. Then that server is simply another publisher in the ICN network of processed data. So this slide contains quite a lot of our findings in this work in one slide. I'm going to summarize them. First, immutable atomic data units. We decided in order to have IoT running on top of ICN without having to change ICN very much, we want to keep the ICN as it is defined currently. Then we want immutable atomic data units. That means all the devices, they produce a stream of measurements, for example. Instead of modeling them as a container with variable content, we model them as a producer of stream of data. Because then we don't get problems with cache inconsistencies. And this has to be connected then to the second bullet, the naming. We want to have a unique name for every piece of data that is produced in this stream. So we add sequence number as an optional part of name. And by doing this, the naming and the streaming, we can separate old and new values by name. We also found under the naming concept that time is very important for sensor data. So we have actually devised a method to map actual clock time to a sequence number. In many cases, this is straightforward. For example, if a device is producing periodic data, then we can have a mapping function from which clock time do I want to which sequence number would that be. So in some cases, it's easy. And the reason why we want to do this is because we then get deducible names that any requester can deduce which name they're looking for. So we don't need the other, like DNS style lookup. We don't need to ask a server first, what am I looking for, and then go and fetch it. You can immediately deduce the name as being requester here. And in order for this to work, the third bullet here is capability and data property advertisement. So the devices or some server tells the world how data is structured from this device, how it's named and how and when it's published. So all the publishers of that kind of data have to adhere to that, and then the clients know. So that all works together. And the advertisements themselves, then they can also be disseminated by ICN. And then we have object security. We have a section on that. I'll skip that now for time. So that was our architecture work. Now, the first commercial proof of concept is in an underground mine. And obviously these PoCs, they're not using all of the concepts that we have considered, but they're using some of them at this stage. This PoC is in operation in Kemi, Finland. It's an underground mine there. It's deployed and supported by Cybercube there, and it's a very challenging environment. And basically what we're doing there is that the data is carried from drilling equipment from the front of the mine by the trucks that are transporting the ore. So the trucks basically act as mules. And currently, each truck will take the data, will request data available and bring it back. So it's quite opportunistically today. It's not an optimal routing, but it works very fine in this context because it's small scale. And this is a large amount of data actually generated. And these Wi-Fi mules on the trucks, they carry the data back towards the control room. And this gives us basically a method to control delay and disruption tolerant opportunistic routing. Why is this important then? Well, it's a mine and they do blasting, you know. When they blast, everything goes away. So the alternative solution would be to roll out wires, or as Per explained, at least you need to place out the base stations. When you blast, you bring them in before you blast, and then you bring them out again. Yeah, you could do that, but with this model, you don't need to, because the points are sitting on the vehicles that will go there anyway after the blasting. So it's Linux on the trucks and other equipment, and there are Windows tablets for drill operators, and there are some GUIs you can follow information, and Android phones for other stuff in the field. Ordinary servers and PCs in the control room. The other PoC is by Futurize. It's in an office environment. It's essentially now and here experience again. It's context-aware services in an office environment. So essentially all the devices like printers and whatever you use in your daily work life would be having an IoT device on it. So you can track them and see whether they're busy, where they are, and so on. You can also track people, if you like. If you want to be tracked, you need to be able to control yourself if I'm trackable or not. By your mobile phone, or maybe you have a little button on your shirt for tracking. And if you want to have a meeting, for example, I need resources, I need a projector, I need resources, I need people. I can quickly set up this meeting using this. It's based on an Android client. There is some Arduino hardware and designs. Also open sourced on GitHub. So it's basically about here and now display. So typically, when you enter your office, you see the resources on current floor where you are now. But I mean, the context can be redefinable. And in this case, context is typically related to geography, but context could be multi-dimensional, obviously. There's an in-memory database, local cloud server based on Node.js also. We have a simulation, emulation. These are more academic for smart city. So to scale this up, we have a scenario for that. It's based on CCN Lite. There is another algorithm to advertise presence of relevant data, to route requests, and keep track of routing. We have an emulation of CCN Lite on Docker containers, recently set up. And essentially here, we use the Docker technology to model the whole network. So every node in this network would be a Docker container of its own. So we can then model mesh topology of CCN Lite relays. We don't know how big it can be yet, but we hope we can have fairly big topologies in the end. We can then randomize selected content sources and consumers. And we adhere to what we explained at the beginning, publishing content as a stream of immutable objects. And we can do a lot of logs in this. Metrics, for example, the number of interest messages. Interest messages means that I'm interested in some data from the ICN, and the number of content objects that are returned, average storage occupancy, and we can look into the pending interest table entries, how many are there, the size of it, latency and hop count, and so on. And we'll show more about this tomorrow, where we have our posters and graphs and so on, showing the actual results. So overall, to summarize this, the ICN is a very interesting topic. It's under pre-standard, as I said. So, but we have all the major companies in there. Besides Ericsson and Cisco, there are Huawei and Xerox and many other. So there's a lot of momentum behind this. So we think that doing this modeling of IoT on top of this coming network technology is very timely. And with that said, our future work is to continue the architecture evolution on interfaces. We have some more work to do on the object security model that we have suggested. More on business modeling. So what's the actual business model to make this fly from a commercial point of view? And more tests and spearheads. So with that, 20 minutes almost consumed. Thank you.